Hello. So in this chapter, chapter 7, we'll be looking at the periodic properties of the elements. We will observe a few trends, one for the size of atoms and ions, one for ionization energy and electron affinity. Now, to begin with, you have to understand the nature of the attraction between the nucleus and the electrons. And we refer to this as the force of Coulombic attraction. This is Coulomb's law, which says that the force of attraction between opposite charges is proportional to the size of the charge, the magnitude of the charge, and inversely proportional to the square of the distance between those charges. So based on this, we know that electrons, which are negative, are attracted to the positive nucleus and repelled by other negative electrons. And the attraction that that electron feels overall depends on both of those factors, the attraction and the repulsion. So we have something called the effective nuclear charge, which is based on the atomic number, but also on the number of electrons that are between the nucleus and that outermost electron. So as a result, you have a size of an atom that is based on that attraction between the nucleus and the outermost electron. So how do they determine the size of the atom? Well, what they can do is they can determine the distance between two nuclei in a covalent bond and then take 1/2 of that distance. What do we observe overall? So we tend to see that as you go from left to right across a period, the size of the atom decreases as the number of protons in the nucleus increase, causing a stronger attraction to the outermost electrons. As you go down within a group, the size of the atom increases because you have a greater number of occupied energy levels and therefore a weaker attraction between the nucleus and the outermost energy level. Now we need to spend a bit of time understanding what happens with the size of an ion. So again, you always want to focus on the nuclear charge and the number of occupied energy levels so that you can determine the Coulombic attraction that's going to exist between the nucleus and the outermost electrons. So the size of the ion is going to depend on the charge of the nucleus, the number of electrons, and then how far the outermost electrons will be, or how many energy levels are occupied in this case. So you'll notice a pattern here. For the cations have lost electrons and therefore decreased the number of occupied energy levels, and that causes the size of the ion to be smaller than the size of the original atom. What about for anions? Anions, you have, then again, the nuclear charge doesn't change, but the number of electrons occupying the outermost energy level has increased, so there's greater repulsion between the electrons, and therefore the effective nuclear charge decreases, or the repulsion is increased, and so the size of the negative ion is going to be greater than the corresponding atom. Cations are always smaller than the original atom. Anions are always larger than the original atom. So, as you go down within a group, you will still see the pattern of the size increasing for the ion as the number of occupied energy shells increases. Let's look at what happens when you have what is known as an isoelectronic series, which is ions which have the same number of electrons. If the number of electrons is the same, then you always want to compare the number of protons in the nucleus. So, sodium, having lost 1 electron, is now gone from having 11 electrons to having 10, but the number of protons is still 11. Magnesium had 12 electrons and lost 2, so it's now 10 electrons, but the number of protons is still 12. Therefore, the magnesium ion is going to be smaller than the sodium ion. Aluminum, 13 protons to attract 10 electrons. Oxygen had an atomic number of 8, so the number of protons did not change. So it now has 8 protons and 10 electrons. So you can see, because it has such a small number of protons, the attraction is weaker and therefore the size is greater. Fluorine, 9 protons and 10 electrons. So the size of the ion is going to decrease with an increasing nuclear charge. So this would be the largest ion, then fluoride, then sodium, then magnesium, then aluminum. Let's move on to ionization energy. Ionization energy is the amount of energy required to remove an electron from the ground state of a gaseous atom. So the first ionization energy refers to removing that first electron from the neutral atom. The second ionization energy would be the energy required to remove a second electron from the positive 1 charged ion. So, as I'm sure you can imagine, it's becoming more and more difficult to remove a negative charged particle from an already positively charged species. It requires more energy to remove each successive electron. So, if we look at this table, the first ionization energy refers to the energy required to remove the first electron to form sodium with a positive 1 charge. The second ionization energy refers to the amount of energy required to remove an electron from sodium ion with a positive 1 charge in order to form sodium ion with a positive 2 charge. Now you'll notice there's a huge difference here because I went from removing an electron from the third energy level to removing an electron from the second energy level. The energy level closer to the nucleus is going to be much stronger attracted to the nucleus and therefore require significantly more energy. Same thing with magnesium. These 2 electrons were in the outermost energy level, which is the third energy level. So yes, it increases from the first ionization energy to the second, but a much larger jump in the amount of energy occurs to remove the third, because I now had to remove an electron from the second energy level. By looking at just these numbers, I would actually be able to tell where that element is located in the periodic table. So I'm looking for a quantum leap or a large change in the amount of energy, and then that tells me that I've actually moved to a closer energy level. What are our trends for the first ionization energy? Well, as you go down within a group, Because that outermost electron is further away from the nucleus, therefore the Coulombic attraction is weaker, that electron is easier to remove and therefore requires less energy. As you go across a row, you have an increase in the nuclear charge, the number of protons, therefore greater Coulombic attraction, and therefore more energy is required. There are some discontinuities you'll notice. There are two areas going across the period where you'll notice that instead of increasing ionization energy, the ionization energy decreases. The first time this occurs is when you're going from group 2 to group 3, and then again when you're going from group 5 to group 6. Why is this occurring? Well, this is happening because in this case, from group 3, I'm removing an electron from the p orbital rather than the s orbital. The p orbital is at slightly higher energy and slightly further from the nucleus. So therefore, it's a little bit easier to remove that p orbital electron. The other dip, which occurs between group 5 and group 6, has to do with removing an electron that was doubly paired in a p orbital. Remember, electrons repel each other. So these 3 electrons that were filled in were all singly filled in. The 4th electron had to be paired with one of the other p electrons, and therefore there was a bit more repulsion due to having the 2 electrons occupying the same orbital. Due to that repulsion, that electron is slightly easier to remove. Finally, electron affinity. That is the energy change that occurs when an electron is added to a gaseous atom. In general, the electron affinity becomes more exothermic as you go from left to right. You can think of this as being because the elements on the right want to gain electrons. So that process releases energy. Again, however, you see 2 of these discontinuities. The first occurs between groups 1 and group 2. The added electron has to go into a p orbital, which, as we said, is of higher energy. That electron is further from the nucleus and feels repulsion from the s electrons. The second time this occurs is between group 4 and group 5. Group 5A has no empty orbitals, so that electron has to go into an orbital that is already occupied, creating additional repulsion. What do we notice in terms of the properties of metals, nonmetals, and metalloids? We notice that metals are shiny, good conductors, malleable, ductile. Metal oxides are basic, and metals tend to form cations in solution. Nonmetals are dull, not shiny. They can have various colors. They can be solid, liquid, or gas, and the solids are brittle, some hard, some soft. They're poor conductors of heat and electricity. Non-metal oxides form acids, and they tend to form anions or oxide anions in solution. Again, we talked about this in the previous chapters. You need to know the pattern for the formation of ions for the metals and the nonmetals, so this should be committed to memory. And finally, you need to know the general properties of metals, nonmetals, and metalloids.